I hope you can see my title slide now. Can anyone confirm?
Yes, we can see.
Awesome, thank you. All right, then let's get going. So welcome to this talk. It's called Integration and Conversation Patterns Foundations. So what I want to talk about today is obviously about integration and conversation patterns. But let me first also provide a bit of a context. So in my experience as software architect, there are two main design principles that you should always consider when you design any kind of systems. And one is divide and conquer, and the other one is loose coupling. And I believe many of you actually apply divide and conquer when you deal with microservices architectures. And I and also many other architects think loose coupling is also very helpful when it comes to designing systems that you can scale and operate, and particularly also evolve independently. And a very good way to reach asynchronous, to reach loose coupling is asynchronous messaging. And this is why I want to talk today about integration and conversation patterns that are mostly based on asynchronous messaging. Like with any approach or philosophy, not only in technology, of course, you always need to consider your particular use case as well. That means asynchronous messaging is not the silver bullet and the solution to everything. It really depends on your particular problem or use case. There are also other integration approaches like HTTP-based APIs or streaming. And you should always make sure that you pick the right one. Today, I want to stress on asynchronous messaging and also use the opportunities here and there to point out why I think it has advantages over other integration methods in certain scenarios. And to put more flesh to the bone, to make it all more tangible, I also brought a few sample use cases so that we can also see those patterns in action. And those sample use cases are in the context of a microservices backend, because we also see when we in AWS talk with customers, they not necessarily have asynchronous messaging on their radar when it comes to integration approaches for their microservices landscape. And speaking of AWS, it just turns out I did not introduce myself in the very beginning, and let me follow up with this right now. So I'm Dirk, I'm a solutions architect with AWS, and in my role, I help my customers on their journey to the cloud. I provide architecture and technology guidance for their cloud workloads, and I try to be their trusted advisor. All right, now let's look a bit at the agenda for today. So I would like to provide a few more sentences, so actually one main point on motivation. And then let's directly dive into a number of fundamental integration and conversation patterns, as I said, mostly based on asynchronous messages. Then I will follow up with some sample use cases. And of course, in the end, I cannot let you go without some resources and a call to action. For the motivation, I would like to directly present this quote of one of our former colleagues, Tim Bray. If your application is cloud native, large scale or distributed, and doesn't include a messaging component, that's probably a bug. I think Tim is absolutely right, but why is that so? Well, if we look at synchronous systems, they come with some inherent problems because by nature, they are tightly coupled, and that applies particularly during runtime. If you imagine your zoo of microservices, most of the time there is some communication going on between them. And if you imagine a request that comes in from the outside, most of the time it will follow a path through your systems. And as long as that request is going on, you bind resources on all these systems that are involved. So that means if there are any problems in downstream systems, they can have an impact on the upstream callers. And then the usual stuff like retries are kicking in. And this can easily fan out and amplify the problems and take your entire system at jeopardy. I mean, in the end, that's why we have mitigation patterns like circuit breaker to take care of this. And in the end, some things simply take too much time to wait, so they are actually asynchronous by nature. All right, now let's continue with actually looking at the patterns. Patterns are a super nice thing for architects and also developers. They are a lingua franca. So if you talk about things and use well-known patterns, then you can make sure that everybody knows what you're talking about. In software development, you're probably aware of the gang of 4 patterns. And when it comes to integration patterns, there's also something that I would call a standard catalog of integration patterns. In the book Enterprise Integration Patterns by Gregor Hoppe and Bobby Wolf, you can, if you want, you can follow this link here, and that will bring you to the website, so you don't have to buy the book or so. You can also have a look at all those patterns at the website. And I want to present now some of the fundamental patterns that we are later going to use in example use cases. And let's start with the very basics. So message exchange, so who is talking to who? And let's start with one-way messaging. And it is quite simple. There's a sender and there's a receiver, but now the decisive part of messaging comes into action, which is the message channel in between. And you can immediately see that this message channel decouples the sender from the receiver. So both parties don't have to know anything about each other. In this case, since it is a one-way communication, there's no response expected. And we can further look at the message intent here. And from a pattern perspective, we can further distinguish between command messages, document messages, and event messages. And as the names say, with a command message, you would send a command to someone. With a document, you would transfer some data. And with event messages, you would notify about that something has happened. And to the opposite of that, we have a synchronous request response. So in this case, the requester sends out a request, message A in this case. It ends at a responder, and the responder responds with a response. So a lot of responding in place here. So obviously a response is expected here. And this might immediately raise a few questions. For instance, how does the responder know where to send the response to? For this, the return address pattern comes into action. The requester attaches some meta information to the message, message A in this case. The responder knows how to extract it from there and uses it to address the return channel. Another question that probably comes up is how can the requester, when a response comes in, know for which original request that response is actually? And for that, the correlation ID pattern can be used. So the requester can add a unique ID to the request message. The responder extracts it from there and also injects it into the response message. And with that, the requester can correlate. And this is also, or let me put it this way, I would also further distinguish in the type of pattern here. So on the left-hand side, we can call this an integration pattern because it's only about how to integrate two parties with each other. On the right-hand side, we also have a conversation going on between the requester and the responder. And this is why we can call the asynchronous request response pattern also a conversation pattern. Now, we have talked a little bit about those message channels already. But now let's also have a look in concrete terms, what message channels are there for us to use? Let's begin with the first flavor. It's point-to-point, and this is usually implemented by queues. So what do we have here? As we can see in the diagram, there's a sender. It sends 3 messages into a queue, and we have even a number of receivers here. So in concrete terms, we can have 0, 1, or more receivers. And the semantics of a queue is that each message is consumed by 1 receiver. And this allows us to have competing consumers in action. And with that, it is really easy for us to scale on the receiver side. That means if there is so much load in the queue that the existing number of receiver processes that I have on the right-hand side cannot cope with it, then I can just add more receivers. And in that respect, the queue also acts as a load balancer. And there's another very important characteristic in a queue. It can usually buffer also messages. So it can even be a buffering load balancer. And that is really a great support to flatten peak loads. So the queue can buffer the excess messages that you cannot or do not want to consume at a given point in time for you, and then you can consume them at your own pace. In this diagram here, I only have 1 sender just to keep the diagram simple, but of course there can be multiple senders. That applies to all channels. Okay, what else do we have? We also have the publish subscribe channel, also known as fan out, and this is implemented often by topics. And the semantics here are a little bit different. In this case, each message is consumed by each subscriber, and the parties are called publisher and subscribers now. So that probably brings an immediate question again. How can we actually scale consumers? If there is so much load in our topic that our subscribers aren't able to cope with that, we cannot simply add another subscriber, because that additional subscriber would add to the problem. It would also try to receive all those messages in the topic. So that doesn't help. And there is a solution to this, of course, and we will park the question for a bit. And deal with something else first. But keep that in mind, and we will resolve the question in a few minutes. There's conceptually no buffering in topics, although concrete products in the market have several sophisticated retry mechanisms that kind of work as a bit of a buffering mechanism, but it can only work for already known subscribers, not for future subscribers. So for late joiners, it will not work. Since we talk about publish, subscribe, and fan out message channels, there's another flavor for it, which is the message bus. And it is a little bit different from how you use it, because usually when you apply a message bus, the scope is a little bit wider. It is usually used for inter-component and inter-application communication. And in this case, usually all the parties that are involved here are both producers and consumers. That's why I have called them prosumers in this case. Also, usually with a message bus, you get additional functionality, but also constraints. Like typically, they support the content-based router pattern. That means they can route messages to consumers based on particular content. They can usually also do sophisticated things like schema validation for the payload, but also force you into a certain format of your payload. And what is quite handy is that concrete products also often come with adapters for third-party software. As I said in the beginning, I will share a few real-world use cases later. And to also better understand the architectures, the concrete architectures that I provide later, I will also introduce now a few concrete AWS services. Since I'm from AWS, my example architectures will also use AWS services. So I introduce you to the services that implement those messaging channels. If we look at the point-to-point channel or queues, we have the Amazon Simple Queue Service or Amazon SQS. It's a cloud-native and serverless message queue implementation. And for the pub/sub, we have Amazon Simple Notification Service, also known as Amazon SNS. Again, it's cloud-native and serverless. For the sake of completeness, but we're not going to use this in our sample architectures because I keep them simple and only use serverless and cloud-native service there. But for the sake of completeness, there's also Amazon MQ, which is a managed RabbitMQ or Apache ActiveMQ implementation. And this is something you would typically use for applications that are constrained to industry standard protocols like JMS or AMQP. And they are also often used for migration scenarios. And again, also for the sake of completeness, there's also a message broker in the AWS IoT core proposition, which supports MQTT, also over WebSocket and HTTPS. But it was designed for the IoT context, but is also quite useful to send push notifications to mobile client. But we're not going to look into this today. And an implementation of the message bus pattern is Amazon Event Bridge. It's again cloud native and serverless. And it is a nice tool for building event-driven applications at scale across AWS existing systems or SaaS apps. So it also comes with adapters for third-party software. Okay, so in my example use cases later, but by the way, I will default to topics and not to a message bus. Because for the understanding of how to decouple systems and using pub/sub with messaging, it doesn't really make a difference. However, I will mention here and there when there is an obvious trade-off to discuss. Now, maybe you have a question now, which is, what about streams, right? We talked about queues and topics and message buses and everything. Why didn't I talk about streams? Well, this is because a stream is something different. It's yet another fan-out pattern, but at least from the way it was meant to be when it was introduced, it comes with a different approach. And I know it becomes more and more tough these days to distinguish between messaging and streaming, because there's also a bit of a convergence of the features. But let's have a look at the fundamental differences between message processing and stream processing, sorry, to make this a bit clearer. So on the left-hand side, let's have a look at message processing. So if you have a look at this picture, which is, by the way, my colleague Christian Müller and I on top of Mos Eisley spaceport, each individual message is a unit of work when you consider messaging, right? So that means from the perspective of every consumer that is involved here, each message that comes in has a meaning, and I want to process it. And then there's a special thing we also need to consider. Every message is deleted after it has been consumed successfully. Now, let's have a look at stream processing in contrast to that. Now, if we consider the same picture, but cut it down into, let's say, 1,000 tiles, all those tiles together would be the unit of work, right? It is batches of messages that are units of work in messaging, in streaming, sorry. So every single message in streaming doesn't add really a lot of value, but the totality of it, like to extract a trend from it, to run aggregations on it, and so on. There's also a fundamental difference when it comes to consumption, because messages are retained in the stream until expiration. All this also comes with an operational overhead. So particularly when it comes to scaling, you still need to do several things manually when you look at streaming systems. And particularly if you compare this to cloud native and serverless messaging systems, There's almost nothing that you have to do manually there. And again, for the sake of completeness, let me also quickly show you the AWS services that implement the stream pattern. So we have the entire Kinesis family as a cloud native and serverless service family. And then there's also Amazon managed streaming for Apache Kafka, which is the managed Apache Kafka. All right, now let's return to the question that we had earlier, which is how can we make sure that we can still scale out on the consumer side when it comes to pub/sub messaging? And at the same time, let's also consider how can we make sure that we don't miss any message while we are not listening, because as we have learned before, topics don't buffer messages, and we might have to turn off our consumer process for planned or unplanned maintenance. So let's have a look again at a message producer. It sends a few messages into a topic. And now we don't directly add the consumers to the topic, but put a queue in between. So we chain a topic with a queue. And this brings us to the comfortable situation that we can then also scale out on the consumer side. And this brings us with the best of both worlds. We have fan out functionality, we have consumer scale out opportunities, and we have the buffering load balancing all at the same time. All right, let's also have a look at a few other interesting patterns in the context of message channels. The first one is the dead letter queue. So again, we have a producer consumer, a certain amount of messages is put into the queue, try to be consumed. And now let's imagine the situation that the consumer always runs in an exception when it tries to process message C. We certainly don't want to have this going on forever, right? And this might be a transient failure. We possibly don't know yet, or it might be a poison pill. A poison pill doesn't necessarily have to be something malicious, but it just means a message that you will never be able to process properly. It will always run into an exception. So what can we do here? We can add a dead letter queue here and instruct the queue system to move the message into the dead letter queue after so and so many failures. And then from the dead letter queue, our application ops team can look into it and inspect. So this is outside of production then. We have no need anymore for an open heart surgery, and we can investigate without the hassle of production. Another technical terms that we also should understand when we look at messaging is our visibility timeout, in-flight messages, and message acknowledgement. And then this is basically relevant for all products on the market there. I will, however, go through it with the example of Amazon SQS. And let's have first a look at a fast enough consumer, and you will shortly understand what I mean with that. So we have the time going on from left to right, and let's assume that tube above the timeline is a queue. So we have a producer that sends a message into the queue. From that moment on, that message is in status stored. Now, a bit later, there can be a consumer who is interested in receiving a message and processing it. It receives message A. From this moment on, the message status is in flight. And also from this moment on, a certain visibility timeout starts. And during this visibility timeout, this message A is not visible for other consumers. So if there was a consumer C2 who also asks the queue for a new message, it will not see message A. Then let's assume consumer 1 is done with processing the message, and now it acknowledges message reception. Acknowledge means in the end that the message is being deleted from the queue, and there are different ways how to do that. For instance, for SQS, you explicitly send a delete message command to the system. And from that moment on, no big surprise, the message status is deleted. Now, what happens if we have a not fast enough consumer? Same scenario as before, message status stored, C1 consumes it, visibility timeout starts, message status is in flight. It's invisible for C2. Now we reach the end of the visibility timeout, and consumer 1 is not yet done with message processing for whatever reason. From that moment on, message status is back to stored and it becomes visible to other consumers. So next time, consumer 2 will receive that message. And then again, the visibility timeout starts. So with that in mind, you want to make sure that you adjust the visibility timeout according to the average processing time that you have. And in the end, it is always a great idea to prepare it on a consumer code for idempotent message processing. Another pattern on the message channels topic is FIFO queues. And FIFO queues, first in, first out, are often said to be required, and sometimes they are even required. And the semantics are that they should deliver strict order for message delivery. So messages in the order they come in, they also should get out of the queue. Order exclamation mark. And obviously, all magic comes with a price theory. So apparently, the more you scale out your messaging, the more it also becomes difficult to impossible to guarantee a strict order for your message delivery. And this has nothing to do with technology or code quality. It's rather the law of physics. And if you want to guarantee strict order, you need to reduce the concurrency and or the scope. And that is why FIFO queues cannot have the same throughput as standard queues. And also there's another pattern that helps reduce the scope also. We will inspect it in a bit, but first let's have a look at what actually can happen when you now have multiple consumers on a FIFO queue without any other mechanism to support this. So if we have multiple consumers on a FIFO queue, concurrent message consumption comes into play again. And let's quickly run through that scenario here. So we have messages A, B, C, D. We have 3 consumers. The FIFO queue delivers them in order. Message A is being processed, message B is being processed, message C is being processed. Now it turns out that the second consumer was quite quick with processing message B. And in our protocol, it appears as the first one. Message D follows up now, and all the other messages are being processed. And some take more time, some take less time. So what we see in the end here is that we did not retain the order in our protocol because the message processing time can vary. And that can lead to order violation in our consumer processes. A pattern that can help here is the message groups pattern. And message groups are, you can consider it as a discriminator attribute that you add as meta information to your message. And the example that we're going to play through now are the message group IDs in Amazon SQS. To keep it simple, let's keep it to 2 consumers this time. We have, again, 4 messages, and the color should express now the message group. So we have the blue message group, the green, and the red one. Message A is delivered as the first, apparently. Then message B is delivered, and they are being processed now. Again, it turns out that message B is processed quicker than message A. And now, this is the important factor here. Not message C is delivered as the next message, but message D, because message C is the same message group as message A, which currently is in flight. And with that mechanism here, with message group IDs, we make sure that no message is being delivered to a consumer for a message group where there is already one other message of that message group in flight. So this is the reason why message D comes first now. It's being processed too. Now message A is done, and we can now continue to also deliver message C. Okay, then everything goes on, and the final result here is, well, we didn't retain the global order, but what we made sure is that we retained order within each message group. That also means we can scale out our consumers according to the number of message group IDs in this example. And as I said already, we didn't retain global message order, but local message order, local referring to message groups. What if a global order is needed for whatever reason? Well, then you need to fall back on one message group, on one global message group for all messages. And that obviously degenerates into sequential processing. Since we spoke about FIFO queues, let's also quickly touch FIFO topics. So we don't have to deal with concurrent consumption here anymore, because every consumer is receiving every message anyway. And the question maybe that comes up is here, what happens with topic queue chaining? The good thing is, if we look at SNS and SQS chaining, they both use the message groups pattern. And from that perspective, we don't need to do anything. It's just being forwarded and taken care of us. All right, quickly also through a few message routing patterns. And I wanted to mention the message filter here to just show how certain things are much simpler when you use messaging. So when it comes to topic or publish subscribe messaging, we said that all subscribers want to receive all messages. But then there are maybe some cases where some subscribers are also only interested in a subset of those messages. And you could create separate topics for all of them, but that would add unnecessarily more management overhead. If you apply the message filter pattern, every subscriber could just instruct the topic, hey, I'm only interested, for instance, in green or in red messages. Publisher, of course, remains totally unaware of this, and it's all controlled by the subscriber. Now, if you wanted to implement this by hand without messaging, you could make use of the recipient list pattern, but that means there's additional code and additional components that you need to maintain. And you would also potentially add coupling between left and right-hand side. So more effort, more coupling. It's way easier to do it with messaging. And one last pattern on the message routing, from the message routing area, the scatter-gather pattern, which is one of my favorites, and I also have a use case for this. It deals with the questions how to distribute a request to relevant or interested parties and capture their individual response. And you would probably use it for election processes, processing scenarios, and so on, when you want to get the best or an accumulate of the responses. So we have a requester that sends out messages into a topic. Then there's a number of potential responders. They can individually work on their response, send it back into a response queue. And then on the requester side, again, there's an aggregator that aggregates those response messages and a processor to process the final result. And that's actually a good example for the beauty of a pattern language. Like if you talk with somebody who also knows the scatter-gather pattern, you immediately have that architecture on your inner eye without the need to further explain it. And we will have a nice use case for this later. Okay, and speaking of use cases, now let's actually continue with the use cases. And the context for the use cases is Rydes, which is a fictional technology startup that we use in AWS for a number of workshops also and sample use cases. It is quite disruptive because it replaces traditional taxi cabs with unicorn rides because it's much more fun and, of course, much more magical. And they have a modern software architecture. They have a microservices backend, and they shared a few of their use cases with us and the architecture for it. Let's have a look at the first use case, submit a ride completion. So imagine a unicorn has just dropped off a passenger. It takes the Rydes unicorn app and pushes a button. Okay, I have dropped my passenger. So what does happen in the background? The app probably sends a post request to the ride management service with all the details about the ride. The ride management service probably has something like a managed API gateway, and then some code that processes the incoming request, stores it in a database, creates a new API resource, and returns to a one created with a representation of the new resource and probably also a link to it. Okay, so far so good. But let's have a look what can happen also internally, because we can easily imagine that there are a number of other services interested in this information, like the customer notification service, accounting service, loyalty service. Of course, there has to be something like a data lake ingestion service and the extraordinary Rydes service. And this one is quite special because it's only interested in rides with a fare or a distance above a certain threshold value. Now, big question, how can we integrate all this with each other? First question is maybe via database. The ride management service already has a database there, so all the other services could simply connect to it. I don't know what you think, but I'd say rather not. This is a perfect example of super tight coupling. And I actually like to call these cases lousy coupling, because it is quite obvious that it will lead to problems in the future quickly. As soon as you do any change in the database schema on the left-hand side, you will break the integration with all the other systems. And I usually, in this context, I think of an article that Roy Fielding has written about a certain REST API that was said to be a REST API, but it actually was a tightly coupled thing instead of a REST API. And what he said is that the architecture on screen provides so much coupling that it should be X-rated. And that applies also to this architecture here. So plain integration cases shouldn't be done via database sharing. But if you as an architect have to explain this to your developers, do it with empathy. That's why the red traffic light here has the shape of a heart. There are a few reasonable use cases for it, like for legacy workloads also, where you cannot set up any integration via messaging or anything else, or streaming also, because you cannot add something to the code. It's super helpful to use like CDC for it. But other than that, it is really tough and you shouldn't do it. Next question, integration via REST APIs. I just spoke about Roy Fielding. So REST is based on the web architecture, and it is apparently the web is a loosely coupled system, and it's also a big one. So yes, absolutely, it works, but it comes with a bit of an overhead effort, right? So we are back to the recipient place pattern, because the completed Rydes processor or any other component that you add on top needs to know who is interested in receiving those notifications. This has to be maintained, and again, additional code that has to be operated and maintained, and also particularly, also potentially more coupling is involved. Again, you also would have to implement that filtering functionality manually also on your own. Let's see, what else do we have at hand? Well, big surprise, integration via messaging. Yes, absolutely. And it's super simple here. You can just add what I have called the ride completion topic here, a messaging channel, a pub sub channel, and all the other services on the right-hand side can just subscribe to it. And that's all what you have to do. Also, the filtering for the extraordinary Rydes service is quite simple. If you use Amazon SNS, you can use the message filtering functionality, or you could use a message bus like Amazon Event Bridge and use the content-based routing functionality here. And these filtering or content-based routing functionalities are available in virtually any messaging product. And if you also want to add more resilience to it and allow for consumer scale out, you can apply the topic queue chaining pattern here. Okay, let's have a look at another use case, pre-booking campaigns. And this one puts some light on the question, how can we use messaging to decouple even parts of a service internally in order to support massive scale and availability? Now, let's have a look at the situation. Rydes runs massive campaigns with a call to action, book your ride for next week already this week. So this time it's the Rydes customer who submits their booking for next week. It lands in the Ride booking service. Again, there's some processing resource. We store it for sure, and we respond to the client. So that's all good. We can handle it with the load and everything. Now, there's a new campaign with a call to action, book your ride for next week already today. This is now the time where we expect a lot more traffic coming in at the same in the same time span. So we try to decouple a bit internally. The ride booking service is again in action and receives the message from the client. Now we have the pre-booking pre-processing resource, not the processing resource. And what it does, it accepts the request and forwards it into a messaging topic, and then immediately responds to the client, this time with 202 accepted, stating to the client, hey, we have accepted your request. We are going to process it now, but no worries, we have it. And then we can decouple the actual reception of the request and the actual processing of the request from each other. Just for the sake of completeness, I have added another consumer who is interested in those pre-booking requests. And I'm going to use it also now to show at the end of this example to show you why I would rather use streaming for the data lake ingestion service. But let's park this for a bit. Of course, still there would be a database attached here, but I didn't have space for it on the right-hand side. Now, let's go even one step further. We now run a massive campaign with the call to action, book now. So at this very moment, book your ride for the next week already. So this brings us to the expectation of a massive load immediately. And what we can do here is to put a queue in front of our pre-booking, pre-processing resource that can flatten the peak load for us. And we could directly expose that queue to our client, but then they would have to speak the, in this case, the Amazon SQS API, which is acceptable if you are the owner of your mobile client. But if you want to open your API for third parties, you probably would not want to do it, but rather continue exposing an API in the same look and feel as for the other functionality. Hence, again, you put a managed API gateway in front of it, and the rest remains the same. Now, a word on the data lake ingestion service. So unless you really do sophisticated, crazy things on all those messages that come in before you want to store them in your data lake, which you shouldn't want to, you don't have to have a particular service for this also. I would rather recommend that you attach an ingestion stream directly to your pre-booking forwarding topic that just drops all the messages in the raw data tier of your modern data platform. Okay, I have one last use case, as promised, the scatter gather pattern. Here it is once more. What we want to do here is that, Rydes is a quite progressive company, and so are the customers. And they don't always want to book or take the unicorn that is just around the corner. But sometimes they also want to run a request for quotes with the unicorns that are in close vicinity, and then just pick the one that provides them with the best offer. And that can be lowest price or maybe other goodies like free drinks during the ride. And again, the customer takes the customer app, submits the data that is relevant for running such an RFQ. And the ride booking service takes this request, again, through an API gateway. It ends in the RFQ intake processor, where it then is stored also, obviously. and then forward it to the RFQ shared topic. Now, we can directly answer to the client with 202 accepted again, because this is a long running process now. Let's say we give 5 minutes for every unicorn to come back with a quote. And yeah, therefore we immediately answer, okay, dear customer, we have accepted your request. We are now working on it. We give you a link to refresh the status resource that we have now submitted to you. What happens under the hood? Now, let's imagine we have the unicorn management service where there is a resource for every unicorn in vicinity. And all these UMRs listen to that RFQ topic. And they can then send push notifications to the physical unicorns that belong to each of those unicorn management resources. The unicorn receives the RFQ, can work on their particular response and send it back to the UMR. The UMR then feeds everything in the RFQ response queue. From there, it is being aggregated and also added to the RFQ store. What can the client do in the meantime? Well, they can retrieve a status update. So we have seen before, there's the link to refresh in the response. So a client can send a GET request to the link, to the URL. It ends in the RFQ result processor. It can check in the database about the current status. Is the RFQ still running? Do we have answers already? And so on. It responds with, okay, currently it's still running. What else can the client do? Well, it can retrieve another status update if they want in between. And this time, oh, status is done. That's nice. So what can we do next? We can retrieve the RFQ result. So retrieve the actual details that we have assembled in our RFQ process. And as you can see here, we have the right data and the quotes. Now, you would for sure also want to add push notifications here to also send a notification to the client once the RFQ is done, once the time is out. But then also you don't want to not give the customer the opportunity to check about the status in between, right? Okay, so these were the use cases I wanted to share with you today, and quickly a few resources and call to action. If you want to read again about those use cases and the patterns from this talk and a few more even, you can consume this AWS blog series here. If you're interested in actually get your hands dirty and see how those use cases can be implemented, you can go through this workshop, Decoupled Microservices. And by the way, Christian and I are going to run this workshop tomorrow here in this conference at 9 a.m. All right. And then, of course, you can always reach out to your friendly AWS solutions architect if you're an AWS customer, apparently, if you want to discuss your integration problems. And one thing to always keep in mind, right? Loose coupling is always better than lousy coupling. And with that, thanks a lot for listening in today. Please feel free to reach out on Twitter or LinkedIn if you want to discuss your integration problem. I'm always happy to do that. And I'm also going to look at questions that are in the chat now and answer them asynchronously. Thanks a lot and bye-bye.